Okay, so on the bell work, it says solve the quadratic equation. So in this case, we're looking for zeros. Okay, we're looking for roots or where it crosses. This comes from the non-calculator part of the SAT. So in this situation, we wouldn't be able to necessarily just plug it into our calculator, find the zero. But if we look at this, this is a factorable equation. So I don't have a negative a value, so I'm good there. I can factor out the greatest common factor, which in this case would be 4. So 4 factored out, that makes that to x squared minus 2x minus 3. Once again, this is all set equal to 0. And then I can use my box that you learned in Algebra 2 or however you factor. We can factor this trinomial. So I do it by the box method. So I'm going to take this x squared, that goes in the top left corner. My value for c goes in the bottom right corner. I'm going to multiply these two to get a negative 3x squared. And I need to find two numbers that are going to multiply to equal a negative 3x squared that are going to add to be a negative 2x. So in that case, they're going to be negative 3x and an x. Okay, negative 3x plus x is negative 2x. Multiply those, I do end up with the negative 3x squared. Okay, so now I want to fill out my box. So looking to factor my columns first, I have x squared and x. And remember, I'm factoring out the greatest common factor between those. Okay, so and that's just going to be an x. And then negative 3 and negative 3. I can take a negative 3 out, x squared and 3x. Once again, I can only take the greatest common factor of x out. And then 1x and negative 3 gives me 1. So if I look and I double check myself, 1 times a negative 3 is a negative 3. Negative 3 times x is 3x. X times x is x squared. And x times 1 is 1x. So at this point, I have it into binomial terms. I have it broken down into my binomial terms. And what I want to do with these is I want to set these equal to 0. So I have x plus 1 as a binomial set equal to 0. And then I'm going to solve them for x. So in order to isolate the variable, I have to subtract 1 from both sides. And I'm going to get that x is equal to negative 1. And I have x minus 3 as my other binomial term. If I set it equal to 0 and isolate the variable by adding 3 to both sides, I am left with x is equal to 3 and x is equal to negative 1, which should correspond to letter B of your multiple choice questions. Okay, so once again, this comes from the non-calculator part of the SAT. So a calculator is not an option. It is basically a requirement that you have something to grade on or graph on. Not grade, that's my job. You guys graph. So my preferred one is the TI-83 or the TI-84 calculator. Okay, I like this because if you get familiar with it, you can use it during the SAT and during your standardized tests. Okay, so this is the preferred one. They're about 90 bucks if you don't have one. I bought one when I was a junior in high school, and I used it all the way through college. I still use it. It's a very good calculator, although it's a little bit expensive. Next thing, Calculator X on your iPhone or Android. Okay. If you go to your app store and type in Calculator X, it'll show under Calculator X84. This is nice because it functions the same way as a TI-83 and TI-84. So you can do like all of your trigonomic functions. So that will that'll make your life easier as we get deeper into pre-calculus. Okay, the third option Once again, this is probably the easiest one for you guys to have access to right now. It's called Desmos Graphing System, and you can see that it's just at desmos.com. So if you come to your browser, type in desmos.com. Yeah, I'm going to leave that page. Bring you to something like this. You just click Graphing Calculator, and it'll take you to the graph. Okay, I say this because we're talking about functions that have high level of algebraic properties and a lot of arithmetic in order to solve. Okay, I know that technology has made my life more efficient, so use the tech to make yourself more efficient, but you got to know how to use the tech. Okay, is the key thing. If you don't know how to use technology, technology is useless for you. But we're going to talk about all three of those. Those, simply put, are going to make your life easier and easier today. Okay? So here's what we're talking about. So in lesson 1.2, we found the domain and range. We talked about symmetry of functions as well. Okay, now what we're going to do is we're going to use limits to determine the continuity of a function and apply the intermediate value theorem to continuous functions to approximate zeros and give intervals where a zero will occur. And then we're going to use limits to describe in behavior of functions. So that's the limit as f of x approaches infinity and negative infinity. Some of these words should sound pretty familiar to you because we did them in Algebra 2. We're going to talk about them. And like I said, this section is a little tough. Okay, it's not necessarily the easiest section in the world because it makes sense at a very high level, but they're asking you to dive down deeper, and the deeper you go, the more complex it gets. Okay, if that makes any sense. Your new vocabulary, we have continuous function. Okay, that's a function that doesn't break. It doesn't have a jump discontinuity. It's not undefined. It has no imaginary values that are present. It is continuous all the way through, meaning that for all the values of the domain, we will have, or the domain can be all real numbers. We're going to talk about a limit. Okay, the limit is, everybody's heard the saying, I was so close that I could taste it, or so close that I could touch it, when they're describing whether it's a monument or a situation. Limit is kind of the same thing. It's where we're getting so close to a domain value, but we're not quite to that domain value. And what that allows us to do is it allows us to estimate what the value would be for that domain. Okay, we're going to talk about discontinuous functions. Okay, these are functions that have breaks in them or jumps in the graph. An infinite discontinuity, it's where you have a reciprocal function where you're dividing by x and you have an area where your graph becomes undefined. You'll see that our first one is an infinite discontinuity. A jump discontinuity is more or less like a piecewise function. Okay, where your graph continues on and then it jumps to another point in the range. You have a removable discontinuity. A removable discontinuity is where the graph continues to go, and then there's just a certain point that's undefined, but then your graph picks up, so your limit will approach the same value. And then we're going to be talking about in behavior as well. Okay. So for limits, what we have here, the words, if the value f of x approaches a unique value of L as x approaches C from each side, then the limit of f of x as x approaches C as L. Okay, and you can see how it's described here. Okay, it's saying limit of f of x as x approaches C is equal to L. So here's our value of C. You can see that they started at x1 and they move closer. Okay, and then they go to x2 and they move closer again. I don't know if you guys can make it out, but there's actually a hole at the x value of C. But using these limits, because our graph is a removable discontinuity, we can estimate if we were to take the x, if we were to be able to plug C in, we'd be able to estimate what f of x is. So we're moving closer. Okay, and then on this side, they start at x4 and x3, and they move this way. Okay, and then the symbols. The limit as x approaches c, f of x is equal to L, which is read as the limit of f of x as x approaches c is equal to L. So what this looks like is we want to be able to approach from the left and from the right. So as you're approaching from the left, your limit symbols are the limit as x approaches c, and there will be a negative there, is equal f of x, forgot to put that, f of x is equal to L. As we're approaching from the right, okay, the negative, because the negative x coordinates are on the left side of the graph, we're approaching from the left side. And then the right is the limit of f of x as x approaches c, positive, with a little plus sign, is equal to L. And then I'm also going to be talking about in behavior. Once again, in behavior, you're talking about the very farthest, if this is the origin of the graph, we're talking about items that would be way over there, all the way to a positive infinity, and then the origin all the way to a negative infinity. So when you're talking about left-in behavior, the negative side of your x value, your symbols are the limit of f of x as x approaches negative infinity is equal to L. Okay, and the limit of f of x as x approaches positive infinity is equal to L. These are your in behavior or in behavior limits. Okay, those are very they're very common symbols. You'll want to get very comfortable with them because, like I said, standardized tests, that's the way that they get presented to us. Okay, once again, as x approaches negative infinity, it's talking about the origin working this way, all the way to a negative infinity. Always talking about a domain value here and a domain value here. Positive infinity, our origin is here, it's working this way. What is the graph doing as it goes farther and farther right as a positive infinity? And what is the graph doing as it goes farther and farther left? As we're approaching a specific point from the left to the right, this C would be the x value that we are approaching. Okay, the negative means that we're approaching it from the left side, and L is what the value would be of f of x if we could plug C in. From the right side, x approaches C. The plus means that we're approaching coming this way. So from positive x values, once again, C is just a domain value. L would be the output of f of x when we are plugging C in. Okay, so important symbols to understand because they are vital when you're talking about the continuity test. Because one of the steps of the continuity test is, does the limit exist? And the way we prove it is we approach it from the left and from the right. So those are limits. Now we have the types of discontinuity. Okay, a function has an infinite discontinuity at x equals c if the function value increases or decreases indefinitely as x approaches c from the left to the right. So here, to describe this infinite discontinuity, we would have the limit of f of x as x approaches c minus. See, as we get closer and closer to c, our graph shoots down to a negative infinity. Okay, in the arrow, we have to assume that that graph continues to go. So we'd approach from the left side to a negative infinity, but then as we approach from the right side, we also approach to a positive infinity. And since our output values are a negative infinity and a positive infinity, it's what's known as a infinite discontinuity. Okay, understand that these can be flipped. Okay, this could be up here. We could do a y-axis, flip it across the y-axis, and have our graph approach positive infinity from the left and continue to go up, and then approach negative infinity from the right. Okay, but the key thing is, for an infinite discontinuity, as we get closer and closer to C, one side of our graph goes to a negative infinity and one side of our graph goes to a positive infinity. Okay, a jump discontinuity at x equals C. C is here, and like I said, this is like a piecewise function. Okay, where they've cut off areas of the domain where C is encompassed in one but not encompassed in the other. So a function has a jump discontinuity at x equals C if the limits of the function as x approaches C from the left and right exist but have two distinct values. Okay, so they're not going to a negative infinity, they're not going to a positive infinity. They're approaching a certain value of L from our limit symbols, but the values of L from the left is different than the values of L from the right. And then our last one is a removable discontinuity. A function has a removable discontinuity if the function is continuous everywhere except for a hole at x equals C. So this would be like a function where it's only undefined at a given point. Okay, but we're still approaching the same value as we move closer from the left and closer from the right. So removable discontinuity, the value of L in our limit symbols are going to be the same. Here, jump discontinuity, the values of L are going to exist, but they're different numbers. Okay, and they're not positive infinity or negative infinity. And then infinite discontinuity, as we approach from the left, we get a negative infinity, and as we approach from the right, we get a positive infinity, or vice versa. Okay, so the three types of discontinuities, you will have to identify these. Okay, and you also have a copy of the PDF associated with the lecture assignment. All of this information is in there. Okay, so here is the continuity test. It has three very distinct steps. It says a function f of x is continuous at x equals C if it satisfies the following conditions. Once again, C is just an element of the domain. Okay, it's a given x value on most of the problems that we have. So a function is constant. The first step, f of x is defined at C, that is, f of C exists. So to put that in layman's terms, if we were to plug in C, we would get a value of f of x. We're not going to get an undefined function. We're not going to get an imaginary number. Okay, so it's defined at C. So once we plug C in, we get a value for f of C. The second area, as f of x approaches the same value from either side of C, that is the limit as x approaches C, f of x exists. Once again, as we approach from the left, it's approaching the same value, and as we approach from the right, it's approaching the same value, which would be kind of similar to how this would be, except for since f of C exists, we don't have the hole. Okay, so they're approaching the same value as you move from the left and to the right, and from the right. Okay, and then the value that f of x approaches from each side of C is f of C. Okay, that is the limit as x approaches C, f of x is equal to f of C. Okay, so more or less, the third condition is based upon these first two. If f of C exists, and as we approach it from the left and from the right, we should get f of C. Okay, for our value of L. And that is your continuity test. We are going to be using it right here. Okay. Identify a point of continuity. Determine whether f of x is equal to 1. F of x is equal to 1 divided by the quantity of 2x plus 1 is continuous at x equals 1/2. Justify using the continuity test. Okay, this is where your technology allows you to do this very quickly. Okay, I believe it was in section 1 or lesson 1.1, we were able to plug in 1/2 in for f of x. And once we do that, we're going to get 2 times 1/2 is equal to 1. We're going to get 1/2. Okay, or f of 1/2 is equal to 1/2. This is the technology part because it makes your life simple. Within Desmos, okay, and I'm going to be using Desmos today because it makes our life simple. So I have 2x plus 1. If I graph that, I can get a good estimation about what I'm looking at, right? Just simply by graphing it. You can see as I approach from the left to go down, my graph goes down to a negative infinity. And as I approach from the right, I go to a negative infinity. So this is an infinite discontinuity graph, but we have to be very careful about what the question's asking us. It's asking us to identify the point x at, is it continuous at the point 1/2? Okay, so if we look at where my discontinuity is, my discontinuity is over here as a negative, and then the value for a half is going to be right about here. The cool thing with Desmos is it's very easy to zoom in. You can click here, up in the top left. So now I have the x value 1 and -1. And if I zoom in even farther, it should show me a grid line for 1/2. There it is. Okay, so this is the point that we're talking about. We can see visually, yeah, it's continuous. But using the continuity test, we actually have to carry out the algebraic steps. Jordan, that was like 30 minutes ago, bud. You're a little late to the party. Okay, so here's our point 1/2, and we want to make sure and prove that it is continuous at this given point. So we have to run the continuity test. Okay, the first step, we need to make sure that it exists. Okay, the way we make sure that it exists is we're going to plug in 1/2 into this equation. Okay, does f of 1/2 exist? When we plug that in, okay, 2, so we plugged in 1/2 for x. 2 times 1/2 is going to be 1. 1 plus 1 is 2, so our denominator for our answer is equal to 2. So f of 1/2 is equal to 1/2. So we get an answer. It's not undefined. It's not an imaginary number. Check. The first condition has been met. You're good. You're good. Just make sure you get your self eval done. Okay. So once again, we're plugging in 1/2 in for this x value. We're carrying out all of the arithmetic. 2 times 1/2 is 1, plus 1 makes our denominator 2. So f of 1/2 is 1/2. It's defined. It exists. It's not undefined. It's not an imaginary number. So we are good. We passed the second. So now let's look at the second part of the continuity test, which is as we approach from the left and from the right. Okay, so does it exist? Okay, the way that we do this is we construct a table. You can see coming from the left to the right, from the left, and here's 0.5 or 1/2. You can see we go from 0.49, which is just a 100th away, but then we go to 0.499, which is 1,000th away, so getting even closer. And then we go to 0.4999, which is getting even closer. To construct the table, this is where your technology makes your life easy. Okay, in order to construct this, if we didn't have technology, we would have to plug each and every single one of these into our equation. We can do it very quickly and very easily using Desmos. Okay, so I come here and I click on my graph and I'm approaching from the left side. You can see I'm at 0.306. And I just keep moving and I get closer and I get closer. 0.46, 0.47, 0.476, so getting even closer. And you can see my y value, which is the right value on the coordinate pair, it gets closer and closer to 0.5, the closer and closer I get to 0.5. Okay? You can adjust the step values here to allow you to increase more and more. Desmos, when in regards to a trace function, it's kind of tough because it really only goes down to the thousandths. That's why I like this, the TI-83, because I can actually plug in, I can go trace 0.49, and then I can go trace 0.499. Then I can go trace 0.4999. Okay, and I can keep entering those, and it's going to spit out different y values. But the key is we're getting closer and closer to 0.5, the closer and closer we get. So working on the left side is this side of my table, working from the left. Okay, and as you can see, working from the right in, once again, they start at 0.51. That's 100th away. Then they're 0.501. That's 1,000th away. And then they're 0.5001, which is 1,000,000th away. So we're getting so close to 0.5, and you can see my y values or my outputs are getting closer and closer to just simply 0.5. So how we would describe that and what that shows is that the limit, using our symbols for this specific equation, the limit of f of x as x approaches 0.5 from the left is roughly 0.5. Okay, or is approximately 0.5. And that's because the closer and closer we got from the left, we were getting closer and closer to 0.5. We can't really say that it's going to be equal to 0.5 because there's a chance that if we were to plug in 0.5, we would have an undefined answer. But the limit does exist. And then the limit of f of x as x approaches 0.5 from the right is also equal to 0.5. Okay? And then if you remember from the first step, we already proved that when we plug in 0.5 into this equation, we're going to get 0.5. So that is the third step of the continuity test by passing the first two steps. The limit exists, okay, or the value of 1/2 exists. And as we approach from the left and to the right, we're approaching what that should be. So, and that's what the table proves. Okay, and once again, technology makes your life easier in this case. Oh, come on. So now we're off to the third step. Okay, the pattern of output suggests that the value of x gets close to 1/2 from the left and from the right. F of x gets closer to 1/2, so we estimate that the limit of f of x as x approaches 1/2 is 1/2. Always break it down into a left or a right because that helps identify the jump discontinuity. Okay, don't just write it as 1. And then the third, does the limit of f of x as x approaches 1/2 equal 1/2? And the answer to that is true, because the limit of f of x is estimated to be 1/2, and f of 1/2 is equal to 1/2. We conclude that f of x is continuous at the x value 1/2. The graph below supports this conclusion. Okay, so like I said, I always graphed it first because I want to be able to use that trace function to build my table. Okay, it's not enough to just look at the graph and say, oh, well, I can see it visually that it exists. Okay, because anytime we're graphing, we're using an estimation. I know I'm killing you, Miss Hartzell. Okay, and there's the 3 steps as they break it down. F of 1/2 is equal to 1/2. The limit of f of x exists And the limit of f of x is equal to 1/2. Therefore, f of x is continuous at 1/2. So here we have another one. We have x squared plus 2x minus 3. Once again, the first thing that I would do is I'm going to plug it in. So x squared is plus 2x, right? Minus 3, double check. Perfect. And I'm using f of 1. So if I scroll out, you can see I'm at a parabola, and I'm going to be using the value of 1 here. So first thing, I'm going to scroll in. My graph move. So here's the point at 1. If I click on it, it does exist. If I were to plug in a 1 into this equation, I would be able to get an answer. It's not going to be undefined. It's not an imaginary number. It would be 1 squared is 1 plus 2 times 1, which is 2, makes 3, minus 3, so I should get 0. Okay, so f of 1 is equal to 0. So that passes the first requirement of the continuity test. But now as I approach from the left and from the right, the closer I get to the x value of 1, I should get closer and closer to 0. And you can see that that is happening. Okay, 0.97, I'm at negative 0.11. If I go just a little bit farther right, I'm getting closer and closer to 0 from the left. I'm getting closer and closer to 0 from the right. Okay, so that means that the limit of f of x as x approaches 1 does exist. Okay, so that passes 2. And then step 3 is that the value of f of x, once I plug in 1, is equivalent to what the limit approaches, which is true in this statement. So we could say that they are continuous. Okay, identifying a point of discontinuity. Here we have to use the limits to describe and make sure that we have to use the limits because they tell us what type of discontinuity we have in the continuity test. So it says determine whether the function f of x, which is equal to 1 divided by the quantity of x minus 1, is continuous at x equals 1. Justify using the continuity test. If it's discontinuous, identify the type of discontinuity as infinite, jump, or removable. So you can see the first step, we're going to plug 1 in for x. So if I plug 1 in for x, 1 minus 1 is 0. I'm going to end up with the f of x value of 1 over 0. Okay, that's undefined. It doesn't exist. We can never divide by a 0. Okay, so we failed the first condition of the continuity test. We know it's discontinuous at this given time. Okay, but to identify what type of discontinuity is, we have to use the step 2 of the continuity test, which is to approach it from the left side and approach it from the right side. And if I plug this into Desmos, 1 divided by okay, you can see if I scroll out, here's 1. So as I approach the x value of 1, which is right here from the left side, you can see that my graph continues to go farther and farther down. Okay, the closer I get, the farther away I go. Okay, and you can even scroll out all the way. The book plugs in points like 100, plugs in points like the x value goes like 0.999. You'll get it once you see it. I've talked a little bit much. But as again, I push from the right and I go to a positive. So this to me looks like an infinite discontinuity. But we're going to build a table of values to prove it, which is the second step of the continuity test. Okay, so they start at 0.9, they get negative 10. They plug in 0.99, they get negative 100. They get 0.999, which is negative 1,000. 1, once again, it didn't exist. 0.001, that's a millionth away from it. They get 1,000. 0.01, which is a hundredth, or this is 1,000th and 100th and 1/10 away. So you can see as they approach 1 from both sides, they're getting closer and closer, but our y values are getting farther and farther apart. Okay, so the pattern for the values of x approaching 1 from the left, f of x becomes increasingly more negative. For values of x of approaching 1 from the right, the value of f of x becomes increasingly more positive. So therefore, the limit of f of x does not exist. Okay, and here's the rationale. F of x has an infinite discontinuity at x equals 1. Okay, another way that you could describe it, this portion, this second part here, using the symbols, makes your life a little bit easier, and you want to get accustomed to them. Like I said, you're going to see them again. These are pretty much your first experience. Is the limit as f of x, as x approaches 1 from the left, not negative 1, is equal to a negative infinity. Okay, so as we went farther and farther to the right, our graph went farther and farther up. So it approaches a positive infinity. And as we went from the left, our graph went farther and farther down. Okay, you can see that, but that's the way that you could express it. So that proves that we have an infinite discontinuity. Okay, the second example, letter B, determine whether the function f of x, which is equal to x minus 2 divided by the quantity of x squared minus 4, is continuous at x equals 2. Justify using the continuity test. If discontinuous, identify the type of discontinuity. So the first thing I'm going to do is x minus 2 on the top, right? X minus 2 divided by x squared minus 4. So clear that. So I have quantity of x minus 2 divided by the quantity of x squared minus 4. Okay, and that's what my graph looks like. And I want to be using right here. Plug that in right. X minus 2. Okay. So this is what my graph looks like again. Once again, I'm running it through the continuity test. You can see I'm going to have an infinite one here at negative 2. But I need to work on the positive value of 2. So when I plug 2 in, 2 minus 2 on the top is 0. 2 squared is 4 minus 4 is 0 on the bottom. It's undefined, and f of 2 does not exist. Okay? So we know it's discontinuous at x equals 2. Now it's just time to decide which is the discontinuous. Okay, here I'm building my table of values. You can see as I get closer and closer to 2, I get closer and closer to 0.25. Okay, that's coming from the left and from the right. Once again, I'm getting closer and closer to 0.25. So the limit's going to exist, and the limit's going to be 0.25. okay, or 1/4. But we have already proven that at the point 2, it's discontinuous. So since this limit exists, but at the point 2, we know it's discontinuous, this should be a jump discontinuity, or a removable discontinuity, sorry. Okay, so if the limit exists, but you're undefined at the given point, it's a removable. We're not going to do that one because I'm running out of time. Okay, intermediate value theorem. If f of x is a continuous function and a is less than b, and there's values such that n is between f of a and f of b, then there's a number c such that a, which is less than c, which is less than b, and f of c is equal to n. So more or less, what it's saying, and this sets up to approximate zeros. So we have our a value here, which is less than our a value, or our b value here. There's a point here that falls in between them at c. As long as this graph is continuous from here, the value of n should be between f of a and f of b. Okay, and it makes sense logically. Okay, this is the location principle. This is what allows you to estimate zeros, okay, or give intervals where zeros happen. What will happen is that the value of c, when we plug in c, our n value turns out to be 0, okay, or root. We're just approximating these. Okay, a key thing to think about is we're looking for sign switches. Okay, determine between which consecutive integers the real zeros of f of x, which is equal to x squared minus x minus 3/4, are located on the interval. This, I'm running out of time, so I'm not going to show you on the graph, but first step you want to do is graph the function. Okay, graph the function because it allows you to use the trace value or the trace function so that we can plug them in. Okay, or otherwise you're going to algebraically plug in -2, -1, 0, 1, and 2 because that is the interval that they've given us. Okay, and then we're going to build a table of values. Okay, once again, they got all of these by plugging the x value in to our function. Okay, and now when we're approximating zeros and we want to say the intervals where there is 0, we want to look for a sign switch on our f of x. If we go from a positive to a negative, that means we had to have touched the x-axis. We're not identifying where we touched the x-axis. We're just saying, yes, we touched the x-axis. So here, -2, I got a positive 5.25. -1, I got a positive 1.25. When I went to 0, I got a negative 0.75. So that tells me between -1 and 0, I had to have had an x value where f of x is equal to 0, and I touched the x-axis. As I go farther right, I have a negative 0.75. 1 is also a negative 0.75, so my graph is kind of turning back around. But then as I go to 2, I get a positive 1.25. So once again, somewhere between 1 and 2, I had to have touched the x-axis. Okay, there had to have been a point. It could be 1.5. It could be 1.2. It could be 1.25 as an x value. But somewhere within, between 1 and 2, my graph or my f of x value is equal to 0. Because that's the only way I get from a negative to a positive, or from a positive to a negative. So here's the graph, and you can see my zeros don't fall on a grid line. So I'd have to solve this. It's probably unfactorable. I'd probably have to use a quadratic equation because this one's a parabola. But the answer, there are 2 zeros on the interval between a -1 and 0 and 1 and 2. Okay, and we can get this answer simply from our table of values. Between a -1 and 0, sign switch on f of x. Between 1 and 2, sign switch of f of x. Okay, so when we're listing out intervals, we're looking for sign changes on the f of x. Okay, determine between which consecutive integers the real zeros of f of x, which is equal to x cubed plus 2x plus 5, are located on the interval. Once again, it requires you to plug in each value and each consecutive integer within this interval. So we're going to plug in -2, -1, 0, 1, and 2, and we're going to build a table. Okay, when I plugged in -2, I got -7. When I plugged in -1, I got 2. So that tells me between these 2 points, I had to have touched the x-axis. A real zero falls here, somewhere between these two x values. Okay, as I go farther to the right, between -1 and 0, there's no sign change. They're both positive. So I'm still above the x-axis here. So I get to 1, still above. As I get to 2, I'm still above. So the only real zero falls between -2 and -1. That's what my graph looks like. You can see that. So the answer is the real zero falls between -2 and the -1. Okay, once again, we're not going to do this one because it would require us to, I got like 6 minutes left. So we would plug in each value, each integer value on the interval. So that would be -4, -3, -2, -1, 0, 1, 2, 3, 4. That's why technology makes your life easy. You can do that very quickly, very easily using the trace function or using Desmos. Okay, or using the calculator X trace function on your phones. Okay, graphs that approach infinity. This is the last one. Once again, we're talking in behavior on this one. Okay, in behavior, something that you should be familiar with. You can see from the graph that as I move from the origin to the right, my graph continues and goes up, right? And as I move from the origin to the left, my graph goes less and less, or to a negative infinity. So this is where we're going to use the limit of f of x as x approaches negative infinity, and the limit of f of x as x approaches positive infinity. And then supporting the conjecture numerically, that's plugging in points into our equation again. So it appears that the limit of f of x as we go to a negative infinity is equal to a negative infinity. Once again, we saw that from the graph because the farther I went left, the farther I went down. And the limit of f of x as x approaches positive infinity is equal to a positive infinity because, once again, the farther I went right, the farther my graph went up. Okay, we saw that graphically. Here's where technology makes your life simple. Okay, they start at 0, and then they go farther and farther left and right. They go to a -100, a -1,000, and a -10,000. Okay, and you can see that my graph is just going to keep going farther and farther down. If you know anything about scientific notation, that should be -1 times 10 to the 12. So this would be a -10 with 6 zeros behind it. So that's roughly about 100,000, I think. Yeah, 100,000. Okay, and then I go to 1,000,000, and then I'd go to 1,000,000,000 as a negative. So I'm getting farther and farther negative. Here, as I go from the right, once again, I start about 6, yeah, or 6 places. So yeah, that would be 10,000, 1,000,000, 1,000,000,000. Okay, as a positive. We're going farther and farther positive. We're going farther and farther negative in terms of our f of x values. Okay, and then this is how we would express our answer, talking about in behavior. The limit of f of x as x approaches negative infinity, and the limit of f of x as x approaches positive infinity. Those are requirements. Okay, this one, we can just estimate it. Looks like as we go farther and farther right from the origin, our graph is going to go farther and farther more positive. And as we go farther left from the origin, our graph goes farther and farther negative. So we're looking for one that says the limit as x approaches negative infinity is a negative infinity, and the limit as x approaches positive infinity is a positive infinity. This should be answer A. Ugh. Forgot about this part. Approaching a specific value. Okay. Dang it. I thought I was done, but I'm not. This is the last example I have for you, I promise. Okay. So use the graph of f of x, which is equal to x plus 2 divided by the quantity of x squared minus x minus 2, to describe its end behavior and support the conjecture numerically. Okay. So you can see our graph is discontinuous at certain functions, and they want us to find the end behavior. And as we analyze it, graphically, it looks like it's going to stay upon 0. It looks like maybe drops down without plugging in. I'm going to say that this is going to stay at 0. Once again, I'd build a table, and I would plug in farther and farther negative values and farther positive values. So it looks as if the limit of f of x as x approaches negative infinity is equal to 0. And the limit of f of x as x approaches positive infinity is also equal to 0. Okay, and I'm just grasping at straws going from the graph. Okay, but now I need to support my conjecture. Once again, this is where technology makes your life very, very simple. Okay, once again, they use scientific notation. Whenever you have a negative exponent on scientific notation, that means your graph, you're moving your decimal to the left, or your number's getting smaller and smaller. So here it's 1 times 10. So that it would start here, which would be 1. And then it's going to move about 3 to the left. So you can see, here's my origin, or here's 0, my y-axis. Plug in negative 100, I get a negative 0.01. Plug in a negative 1,000, I get negative 0.001. Plug in negative 10,000, I get a negative 0.00001. As I move from the x value, the y-axis, to the right, plug in 100, I get 0.01. Plug in 1,000, I get 0.001. Plug in 10,000, I get 0.0001. So once again, I'm getting closer and closer to 0 as I go to a negative infinity and a positive infinity for my x values. So as x approaches negative infinity, f of x approaches 0. And as x approaches positive infinity, f of x also approaches 0. So this supports our conjecture. And we can list our answer this way. Once again, in behavior, this is a required thing. The limit of f of x as x approaches negative infinity. The limit of f of x as x approaches positive infinity. The zeros will change given upon the function and or the graph. Okay, that's all I have for you. Like I said, it's stuff that we did in Algebra 2, but it gets a little bit tough.